Hi, in this video I will be introducing the basic principles involved in any AI model training. What happens when we hit loss.backward or model.train in several frameworks. And by this, I am hoping to introduce from the model training perspective what cross entropy that we're familiar with in several machine learning frameworks and the stochastic gradient descent fit. So I will introduce stochastic gradient descent as a way to update models. Of course, there are many derivatives of the stochastic gradient descent, but let's see. Here we go. So let's go ahead and start the model training of AI models. So let's go ahead and open up the boxes, like what we have, what we don't have. If you remember from last week when we discussed an AI model can be deemed as a black box that's inside of which let's write AI here, inside of which we do not know. And typically AI models are going to take inputs of whatever, images, videos, text, sentences. So these are, let's assume that these are brain MRI images, right? And the output, we want as the output for it to tell us cancer or not, or where the cancer is, depending of the problem. So we are talking about an input, and AI model ties it to an output. And we discussed that in a conventional machine learning problem, we are not programming some black box such that it takes the inputs and then yields cancer or healthy output results. Instead, we are parameterizing our AI model. AI model will be a mathematical function that ties input to the output. And this mathematical function will have some parameters, right? So this thing is what we call parameter. So when we call, and this is what we're going to call the model, right? So we are talking about something like this, output that's equal to this model, which is parameterized by this data, and it takes inputs. So there exists a model that's a mathematical function model that takes parameterized this data, that takes input, any kind of input, and gives us the desired output. So I would like to invite you to ask this question. So when we call model.train or model.fit, something magically happens and we get a model that works very well. So this model is the learned, we call it learned parameter set. So in order for training to happen, we know our basic premise is there exists a set of parameter values, call it theta star, that works. Let me write better. That works better than others or other theta values. The phrase that I would like you to focus on is this. Better than. Better than what? Better with respect to what? So that's answering this question is the first attempt in machine learning. So what we want to do is, given a training set and their labels, we would like to do two things. One, we would like to our goal, every single time that you're attempting to phrase or establish a problem into an AI learning problem or machine learning problem for that matter, you need to do one, find a way to tie X to its label. Let me not introduce the terminology yet. The input to the output. So that's number one. And this way, we would like it for it to be parametric. There has to be some things to be learned. And two, find a way to measure the goodness of a parameter set, right? So the first one you might have noticed is talking us to build the model architecture. And the second one, we have a name for this, and we're going to call it a cost. Or specifically speaking, we call it a cost function. So what we want to do is to establish a cost function that ties my input to my output. So if we assume that we are given a training set, so I'm gonna call it X, and let's try to write what my training set. This actually not X, but capital Chi, if you say. And let me put the name. So this is called training set. Whoops, that was bad. Training set. All right, so when we're given a bunch of x's, x of I, r of I, x of 2, some image, r of 2, yada, 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 x of n, capital N, r of capital N, we would like to train our model using this and find a model that's going to work on this data set? No. Find a model that's going to work on a data set that's never seen to you. But we discussed this in much detail recently, but we'll get to that. So we can name these guys as, so this is the input. Actually, this is the ith input, sample, and that's the label. So let's make another simplification. Let's call our label to be, for now, one of the two classes, right? So it's either 0 or 1. So it should be labeled in element of 0 or 1. So let's make it, so let this be the cancer class and 0 to be the healthy class. Don't worry, I just made this simplification for the sake of just tipping our foot into the water, just tasting the waters, and then we will go into classifying more classes, right, at the same time. So the function and another, let me put some with capital large. We write it first. Wow, that was bad. Two classes first. We will do K classes in a bit. All right, so let's make one simplification of our model. Oops. Add a new page. So let's go ahead and draw this. Our model. starts with the image. And this one, this is a horrible brain MRI image. And I'm going to call this X because it is the input. And right now, I am not yet opening up our black box AI model with all of the details. Let me go a little bit 2008 and draw a huge box called a feature extractor. So this is not necessarily parametric. This is engineered. This is a function, right? So this is f of x. And this f of x gives me what I'm going to call h. The letter h comes from hidden, actually, and it's going to become, this notation is going to become more meaningful when we go to deep neural networks. But hang on with me. This h is going to be my embedding. And this embedding, now here comes our AI part. So I would like a neuron, one neuron that's going to understand from this embedding. I'm doing building my first parametric model right now. I'm going to look at each and every one of the dimensions of this h, and I will combine them. And then I will do weighted average of all of them. Right, not weighted average, weighted sum, WD. So this H in R to the D. And then I summon them and I get my Z. So this is, this Z is going to be used for my classification, right? Okay, so far we have built our first thing. So I have my Z, which is going to be some summation of D is equal to 1 to capital D, H of D, WD. So that's my thing. And if you would like to write down in more linear algebra way, it is nothing but an inner product. I'm learning a vector W transpose times H, which is H is obtained by my f of x. Right. So right now, this is my parameters. This is the set of my parameters to be learned. So this parameter, hopefully, is going to take my W, my F, and then give me the output. I am going to make another simplification right now. Instead of asking you, how would you define the measure of goodness? How would you define one W being better than other W in terms of meeting expectations, making Z similar to R? The first thing that can come to mind, which is not horrible, but not ideal for classification. The first goal, we can say, our goal is to make, we want make Z for each and every one of the sample, Z of I, close to R of I. Only then I can say that my model works, right? Very naively, we can think of doing it as such. And also, we can make this by not worrying at first, not worrying so much about the statistical aspects of the problem, but we can minimize. We can introduce an error function. Let's call it E. And I'm going to define this error function. And I want the Z of i's to be very similar, very close to my R of i's, right? So I can take the difference, or I do not, I probably would not want to deal with negative numbers, because like even if my z of I becomes less than my r of I, it doesn't mean that it should reduce my error. I would either put some absolute on the both sides, or mostly I would want to minimize the squared error, just like in regression, remember? And this output obviously is going to be averaged over all samples that we would have. And typically we would write, if we have I equals 1 to capital N, so we have n of them, but we typically put another number 2 here because of the very reason that you will see in a second, which involves derivatives. So when we take the derivative of this 2 is going to come here, and we would like it to cancel. So we can call this an error. And this guy, we call this error, we call mean squared error, right? So MSE. This exists. So, and again, like, where is the model? That's going to be, so like we mentioned, the error should include the three things. One, it should include your training set. So I'm for sure utilizing all of my data set from 1 to capital N, and I am using my labels. I'm trying to meet my labels, and my Z is nothing but W transpose F of Xi, right? So that's what I have. So I have here the things that are given to me. So this is my given and training set. And this guy, this W, is my optimization parameter, right? So this is my parameter. All right, so I would like to, before I move on to the next topic, I would like to pause here and invite you to examine what's happening in this error, right? And we mostly use the letter J for, in papers you will see J for the cost function, right? So cost function. So in our case, our cost function directly becomes an error. So I can say J is equal to MSE, or error that's calculated like this. But before I move on to how to minimize this and how to learn the set of parameters, I would like to invite you to think of it like this. So in the beginning, our data set, this X of n and R of i's, assume that in the H space where I see the H's, right? So H1, H2. So I can go ahead and place all of my data points here. So let's say I have placed my data points with class 0 or healthy class with green, and the other class with red. So there exist several lines that separate the two, right? So this line is one of them. So this is just one of the W's. So I can call this W1, like make it not superscript nothing, and we can actually talk about another W, right? So this can be another W. So let's say W2, and we can say W1 maybe better than, and again, better than W2. So my goal is to find such a W that's for which I can say it is better than everybody else. So that's a difficult problem, because it is going to involve us to see not from the part that we in this optimization problem, not from this, but in a space where all of the W's exist. right? So I'm going to draw another space here. So I'm going to call this W1 and W2. Of course, there are typically these W's are multiple dimensional, right? Like GPT-3, for example, 175 billion parameters. And I'm just writing only two of them here. That takes all of the inputs. And for each and every one of the W pairs, right, going through the data set here, all of the greens and reds and etc., I can calculate this number. So there exists a W number. Let me take my colorful thing for whom, let's say um, this W here, this region, and let me go ahead and mark it. This W maybe, right? So I'm going to call it W star, and so that's W2 star, and that's W1 star. This W can be better than those around him. So you can calculate this error for any of the W's. So very probably this is not going to be as smooth as I am drawing right now, because one can expect a different error number, like this surface, this error surface might not be like this, or it might not be like convex as I'm showing here. There might exist a region where the W's are great, like even what is darker than red? Is this red? No, maybe. Let me use this pink. Maybe this is even better. And if I could get close to this region, maybe I can find a better model and I can draw the rest of the space like this. Like the only reason that I'm like butchering some artsy talent here, because I would like you to see the difference between going from here to here. So this is the future space. So this is a space. Well, maybe like this, it doesn't, it might be more confusing. So from the future space of H1 and H2, we can see that the classes are linearly separable or not. And when we're looking at here, we're talking about the weight space. And this weight space is a space which has as many dimensions as the model that you're trying to fit using your data set. And on this space, there exists surfaces that are calculated, error surfaces that are calculated using your data set. And you are trying to find the regions, one point, that's what you want. One point in this whole weight space that's going to work better than others. And yeah, so that's basically what we're trying to do. But the problem is, in order for you to walk on the space, let alone it's never going to be a two-dimensional space, and you never see that space to go ahead and pick the biggest value, the best value. What you do is you're mostly, because you cannot take the derivative of something that has the data and make it equal to zero. The old calculus talents do not work here. But what we do is we find one location to start with, and from this one location, we would like to go and eventually land in this nice region. So that's what we do, which brings us to stochastic gradient descent. So stochastic gradient descent is very much like the problem that I introduced. You have an error surface, just like this fisherman by himself trying to find the deepest point of the lake. This fisherman is trying to find which point or which weight parameter solves his problem the best. Just like the equation that I showed here, which is again mean squared error, not good for classification. We are going to come back to it, but just like you see, for any kind of weight value, given the data that you have, you can calculate this error. you can do that for any given weight value. You can do that. So you can measure the depth wherever you are. You can go to any place, you can measure the depth there, but you cannot possibly measure all of the depth values any place of this lake. It would take forever. What you typically do is the whole point is wherever you start, you go to some place, and now you measure the depth, and then I'm going to zoom in a second, and now you measure from this point which direction I should go such that it gets deeper. So when I zoom into this part where our fisher just is using 3 measurements, they can understand which direction it should go. And funny enough, the direction that the bottom of the lake goes deeper and deeper is against the direction of its slope, as you see. So when I zoom in, although the bottom of the lake is weird and multidimensional, not convex, not at all, but when I zoom in, when I take the derivative of the point that I'm measuring at that point, at least it can tell me where I should go for a better measurement. And then I go. So here we go. This is our stochastic gradient descent. What you see here is a W, and it has a superscript we call t plus 1. The W is going to update. You're going to start with 1W in your weight space, and from that starting W, you're going to calculate your derivative with respect to the cost. And you see the J here with respect to the cost, and you're going to take a step against the direction. So WT plus 1, the next gradient value, which is guaranteed to be lower than the one that you started with, is the one that you were on minus some step size, nu, times the derivative there. So that's stochastic gradient descent. What we're going to do right now is to calculate the stochastic gradient descent in the setup that we are given. So we are stochastic, the SGD rule. Our SGD rule tells me that I should, my W t plus 1, or let me start from the beginning, 1, I should initialize 1 W0, right? So this is, I start from some W. We're going to start from some W, and there are some rules to where to start these W's from, because if you see up there, wherever I start decides on where I'm going to land, because wherever I start, I'm always following the direction of the steepest descent. And I will be landing in some point according to the cost function that I am calculating, that has some convex hull around it. So I initialize 1W0, and 2, I update my WT plus 1 is equal to my WT minus some step size, and DJ dW evaluated at W equals WT. So my word for this is the step size. And you will see that the step size is going to be important for jumping through the W's as well. Again, you will never, let me write it here, some upsetting fact, you will almost never, but I'm gonna write never, see this space, right? So like this is just a demonstration for you to see what's happening under the hood. Typically you're talking about a very big J, a very big not very big J, but a J that's involved, and the W has a very large dimensionality. So the only thing that you will observe is your J your cost calculated wherever you are. So from your cost that you calculate from at wherever you are, you're going to have a sense of if you are jumping too much, if you're going to some other spaces, if you're not moving fast enough. So this step size is going to be instrumental for you to design your training methodology. And let me add finally three, terminate when error evaluated at w equals wt plus 1 is almost equal to w error equal wt, right? So this is evaluated at, pronounce this, evaluated at. Sorry, my handwriting can be off sometimes. All right, so all I need to do is now, so I have the W, I can count the W, and I will write W equals W minus my learning rate times dj over dw, right? So that's what I'm going to do. And what is my, and one other thing. So typically, dj over dw is defined as dj over dw is defined as my weight displacement or step. So this is my step, and this shows me a direction, and this the step size, or there's another name for this, learning rate. Right. So step size actually decides on how much of your step you would like to apply when you're moving. So let's go ahead and calculate our step. Then we should be done for two classes and mean squared error. Of course, I'm going to change this simplifications, right? So I'd like to calculate dj over dw, but when I look at the j, it doesn't involve the w directly. But what would be simpler if I could use what we call the chain rule. Chain rule I'm inviting from calculus. So chain rule tells us if dj is relevant to our dz, and if dz includes my dw in it, so I can do that. So my dj over dz is d sum equals 1 to capital N, and that's 1 over 2 capital N ri minus zi squared divided by dz times, what was the dz and dy? H transpose y, or H trans W transpose H dw. Okay, so this part, the second part, might look like it involves a little bit of linear algebra differentiation, because this is a scalar and this is a vector, if you notice. But it's quite simple. Let's go ahead and solve the first part, because first part is the simplest. So I can take 1 over n to the outside, because derivation is a linear operation. I can take put it inside the derivative and summation. So I will have I equals 1 to capital N 2 over 2 r of I minus z of I, and there will come one negative from the derivative of this guy, and times. So let's go ahead and introduce one simplicity, right? So let me introduce this one index here, wk. So this is what is wk? Let's make everything scalar. Let's go back to high school, and then very slowly converted into a vector algebra. So this is my kth index of my w, right? So I'm trying to find the wk, the derivative with respect to wk. There's no matrix yet. And let me go ahead and write this part too. Let me introduce, where do I plug it here? So it's wk, and I'm going to delete this and now write this inner product with our high school knowledge. I am just doing nothing but k equals 1 to d wk h of k, right? So that's what inner product is. And when I take the derivative of the first term, I get this, and I can go ahead and cancel this one too. And the derivative for my wk, so my wk, my step along wk becomes like everybody dies, right? Because this wk, actually, it was poor choice of me to use this as an index. Let me, whoops. Right. So my d equals 1 to w2 t h of t, right? Only one of them will have wk in it, and that's going to be whatever k is. K can be 1, 2, 3, 4, and that's going to be multiplied with the h of that index, right? So it's going to be h of k. So therefore my w1 is nothing but summation over all indices I equals 1 to n r of I minus z of I and h of 1. And of course we are talking about, since we are summing through all of my samples in my data set, so my h of 1. And my step towards w2 is the same thing, 1 over n, summation I equals 1 to capital N, r of I minus z of I, the error that comes from upstairs, and h2 of I. So I can go yada, yada, yada. So in linear algebra, since we're talking about a vector, so I'm going to put a arrow on top of it to emphasize that it's an error. It's nothing but summing from all of the indices, which might not actually fit in your GPU. So you're going to use some mini batch or batch. So let's call this sum over a batch of samples. So this n can be, I don't know, something like smaller, m, and of course 1 over n of them, r of I minus r of z of I, whatever the error that it generates, times h of I. So before I stop this part of the video, I would like to mention one thing. I would like you to observe one thing. So when I am trying to learn a W, I am using my best W, the direction. I'm going to start from one W, and this W is going to calculate some output, right? A W for an input. For some input, it can calculate a Z, and this Z is going to be compared with whatever we want it to be. So R is either 1 or 0 in our problem, and I'm trying to push my Z's to be as close to that or not, right? So, and if R is 0, but my Z is not 0, I will be calculating a negative difference here, and therefore adding, I am adding the corresponding H. So one thing that I would like you to notice is that the W's that are going to start from somewhere and get updated, they all go ahead and digest the input that actually was being processed by that W. So that's one thing that I would like you to observe now. And in the next video, we will change this just a little bit. Let me spoil. In classification, we do not use mean squared error. Instead, we approach this problem as approach the data set as a random variable, as samples of random variables, and we would like to maximize the likelihood of my model given the training set. So next video, I will be taking us a more step close to that approach. So far, we have done a very naive approach. We have expressed our AI problem, as an input and a mathematical function, another parameterized mathematical function to the output. So we did our first job. We tied input to output. We defined an error function, which might not be the best and which is not the best for training. And I will introduce what works and what we are doing. But it was a cost function. It's wrong, but it served our purposes of establishing a cost function to be minimized such that a better function can be learned. And by establishing this cost function, mean squared error, we were able to find the set of update rules following stochastic gradient descent, and to eventually land us to a better set of W's. So that's what we did so far. Before I move on to cross entropy, I would like you to I would like to discuss something. So let's say that RH, let me put a lighter one. Let me get it lighter. Let's say RH is a scalar, right? So H, which is the feature, is a scalar, right? So when we have an H, so I have this H, and I can go ahead and place my positive and negative samples with this H, right? Let me go ahead and place, because this is my data set, right? And I am trying to fit a function using this that's going to take these guys. So let's say this is my Z, my output, and I would like for this H's and the samples to go where I want them to. Notice how I am for these H values, how I'm trying to push the Z values for these guys to exactly, like perfectly to be fitting on the zero level. And very suddenly, the moment that I start classifying the other sample, I want them to be exactly one, right? So like this guy is going to be one. This guy is going to be one too. This guy is very one. This guy one also. Like, notice how I'm trying to mark all of them one and mark all of these zero, and I have no patience, no mercy for these guys who are supposed to be somewhere near the decision boundary to be something else. I have no reason, like in this setup, I have no means of representing some kind of uncertainty or some kind of probability. So in our next setup, we are going to regress. Instead of regressing to the actual 1 and 0 values, as in linear regression, our model was a linear model. We learned to weights, and through linear projection, we ended up with 1. Right now, we're going to, instead of regressing to 1 and 0, we're going to estimate, our model is going to output the probability that the sample belongs to the cancer class. Remember, we did 2 simplifications. We did 3 simplifications, actually. One, we did not worry about the feature extraction part. Here, we will break this. Maybe not today, but very soon. The first simplification we did, starting from this, we trained a linear model. That was first simplification. The second simplification was we assumed that we have 2 classes. I'm going to break it after I break the first, this one. And the third simplification we did was we just didn't worry about the probabilistic nature. We just wanted to regress to what we want them to. And therefore, we used the mean squared error as our cost. So next thing, I am going to take this simplification to the actual implementation. But the reason that I did this was to show you in a friendly environment how the input-output matching was done and how we establish a cost function regarding the input and output, and how we train models following stochastic gradient descent, whatever the cost function is, right? And now let's go ahead and make it more realistic. For this, I'm going to start with my training set again. So let's remember, that's my training set. My training set is something like this. I have x1, r1, x2, r2, and yada, yada, yada. Right. So I have this x of n, r of n. And why did I rewrite the whole thing? Just so that I would like you to see that this is my classes. So I have 0 or 1, or this can be 0 or 1. So I have all bunch of zeros and ones. So when I look at the labels, so these are my labels. So instead, right now, let me build my model again. Instead of me emitting at the end of the model the 1 and 0 value directly, why do not I make a model, train a model that predicts the probability of the label being 1, right? After all, I'm trying to estimate that. And if I make it 1, then I am, if my probability, my system's, my model's output becomes closer to 1, I can say I'm very close, getting closer to the label, right? So again, I'm going to draw our X, my ugly looking brain MRI. So that's my X, and my X goes to this feature extractor, right? And I get one H, again, the same way. And I am going to learn the set of weights here, and I'm going to get my Z. But now, I'm not going to use the Z directly. I'm going to, let me write what is inside this little box. I call it a summation symbol because that's what's going on. And on these wires, you have W1, W2. And here, I want some function, some activation function. I'm going to draw this shape here. And from this activation function, I want this to output a probability, right? So I would like my Y, which is which is an output, which is some function. We don't know what yet. I'm going to use this Greek letter sigma, and I'm going to, this Y function takes as input the neuron activation. And this is supposed to, hopefully, going to give me probability of cancer given X. Wait, where is X? It is inside Z, because I get SZ, nothing but W transpose H, which is nothing but W transpose F of X. There we go. Now we have established a set of functions, the future extractor, which is F of X, which gives me H. And I have another function which is now parameterized, and I'm going to learn the parameters, and which is going to give me Z. And this Z is going to be used to give me the probability. The question is, what is this Y, and what am I going to, this Y, I want this Y to give me the probability, right? So first of all, let's go ahead and understand what the function should be. So instead of this time my Z, so that's what I want. Instead of my Z activating, being greater than 0, symbolizing cancer, let me go ahead and write cancer on top of this, and my Z not activating, being less than 0. I drew this horribly. Let me draw it again. So greater than and less than. So if it is less than 0, I can call it healthy. So instead of activation and suppression, instead of looking this, is it greater than 0, less than 0, which is a typical classification rule in perceptrons, like during the time where the perceptron was first being introduced. I want, instead of this, my probability of cancer given X, if this is greater than my probability of healthy given X, right? So I want the two things to tell the same thing. So what I'm trying to do here is to find, let me write this. Let's find the relationship, or find a relationship between Z and Y, such that Y is equal to probability of cancer given X, right? So that's what I'm trying to do. All right, let's go ahead and go this part. So if probability of cancer is greater than X, probability of cancer given X is greater than probability of healthy given X, I can write it in terms of Y. So this is Y. So this is greater than 1 minus Y. So I'm going to try to find a relationship between these two, and vice versa. So like if this is greater than 0, I call it cancer. If this is less than this, if this is greater than this, I can call it healthy. And similarly, I can do the same thing. Cancer can go here, and healthy can go here. I apologize for the mismatching colors. Typically, red colors is used for cancer, but hang on with me, because I'm trying to still find a relationship between these two. So I can go ahead and write y minus 1 minus y over 1 minus y is less than 1 or equal to 1. Then I guess I found the relationship between, so cancer healthy, z and y. So I can take the log of both parts, y over 1 minus y less than greater than, if this activates, if this term becomes greater than 0, I call it cancer. If this becomes less than 0, I call it healthy. Then merging these two things, so this and this, merging the two, I can go ahead and I write here z is equal to log of y over 1 minus y. Then I can take the exponential to the both sides. Exponential of z is equal to y over 1 minus y. So I can, in order to make the calculation easier, I can convert them by the order of numerator and denominator. So 1 minus y, y, then y. So y times, whoops, y times exponential negative z is equal to 1 minus y. Then I have my y, which is equal to this function, sigma z. Now I know what my sigma z is. It's 1 over 1 plus e exponential negative z. All right. So it's like there's one more line here. 1 plus exponential negative z in parentheses y is equal to 1. Right. So from my z, I get this function. Let's go ahead and draw this function very quickly. With respect to z. And this is going to be sigmoid of z, which is y. So I know my z, if my z goes to positive infinity, if I put positive infinity, this becomes 0, 1 over 1, 1. So if my z goes to positive infinity, my score becomes 1. If my z goes to negative infinity, right? So this negative infinity becomes infinite, dominates the denominator. 1 over something very close to infinity becomes something very close to 0. And if I put 0 for z equals 0, it becomes 1 over 1 plus 1. So it's 0.5, right? 1 over 2. So I know I'm talking about a shape that goes from negative infinity and then goes through 0.5 and then makes this shape. So then I am talking about a probability. So if you go farther from the activation, if you score higher and higher, your probability of cancer becomes higher, and as you are on top of the decision boundary of 0, your probability is 0.5, and this region is the part that you can actually report probability. And since this function is S-like, we call it the sigma function. So sigma is the Greek letter S, and we call it the sigmoid function. So sigmoid function, sigmoid, in other terms, it translates to something like S-like, because it looks like an S. It's not exactly an S, but it's an S-like. It's a sigmoid function that takes your activation and gives you your probability. All right. So the next thing that we would like to do, now we did our first homework. We established a model from start to the end. Now this model is hopefully giving me my probability. The fact that we tied it as such is not going to make it perform as such. We need to enforce that it is going to be the probability by enforcing rules from the probability. Now, in order to do that, let's go ahead and check our data set, right? So my data set was, again, the same thing. So I have XR, X1 R1, X2 R2, yada, 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 right? So these are X of n, R of n. So this is my training set. I have random like outputs that are always zeros and ones, right? And with the model output, I get their probability. I get, so if this is R1, my y1, which is my model output, is going to be tell me the probability of r1 being 1. That's it. And my model output for the nth output, nth input, is going to be probability of Rn equal to 1, right? So I'm actually talking about my Rs, my samples in my data set. A person being healthy or cancer, we can call each and every one of them Ri to be a Bernoulli random variable. Remember Bernoulli random variable? Bernoulli random variable had one parameter, and the parameter of it being 1s and 0. So Bernoulli random variable, so I'm going to call it P equals yi, right? So Bernoulli random variable is like the coin toss. And if you have many Bernoulli random variables, you're talking about a binomial distribution. And this binomial distribution has its own likelihood function. So let's try to calculate the likelihood of my data set. So if I told you, before I startle you with words like likelihood that's coming from probability theory, if I told you, hey, I have a set of coins with their own probabilities of 1 being 1s and 0s, and if I tell you this happened, like I did the experiments of tossing the coins, all of them, and these were the results. So given the results, or I shouldn't say given the results, because the word given can take it to the other direction. Looking at what I told you about these coins, their probabilities of turning these coins, can you tell me what is the probability of my experiment? So this is called the likelihood. Let me write. So this is likelihood is, generally speaking, is the probability of your data set observing what you have observed conditioned on the parameter. So likelihood is always testing a parameter that is to be estimated, right? So our likelihood is probability of observing what I have observed, my data set, right? My x1 and its label, my x2 and its label, and yada, 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 all of them, my x of n and its label, all of them conditioned on some parameter. And what is the parameter that gives me gives me the opportunity to talk about my labels as Bernoulli random variables? The parameter that I use is the probability that my model estimates, right? So it's actually conditioned on the probabilities y1, y2, y3, yada, yada, yada. So since these probabilities are actually coming from the x's, all I'm judging here, the only differentiating factor, the only thing that changes is this horrible theta here. That's the model parameter. So since my samples are independent and their probability calculations are independent from each other, the joint likelihood can be calculated as the product of their marginals. So I can talk about I equals 1 to capital N, and then probability of xi, ri, given my model, which actually my y actually uses my xi, so I don't even need the xi here. So here's the part, my likelihood. Let me write it again. My joint likelihood of my data set. The power, I would like to state a few words here. Likelihood, when you write a likelihood, you are tying your data set to a prospective parameter that, or a model that you would like to evaluate. Likelihood calculation is always for evaluation, and it tells you the power of your model describing your data or explaining your data. You say your data set comes from a Bernoulli distribution. Samples from your data set comes from a Bernoulli distribution, and the probability of these things appearing ones and zeros have to come from your AI model. So here I'm going to draw a thinking bubble. Let's remember our Bernoulli random variable. So remember, this is where we remember. So my Bernoulli random variable was a coin toss, right? So I had the probability with P, we probability heads, and why not 1 minus B probability tails, and the probability of heads, and when we make it a random variable, we say we give some real number to these events, each and every one of these events. So we typically call them the capital X, which is for the random variable. And if we were to write the probability mass function of a Bernoulli random variable, we're talking about the probability of X. So this is capital X, this is lowercase x, for any of the x's, lowercase x, is equal to P to the X 1 minus P to the 1 minus X. Why is that? Because if X is 1, then P to the 1P, the other term disappears because 1 minus X becomes 0. If X is equal to 0, then P to the 0 disappears, and I get 1 minus P. So I get my distinct probability mass function for Bernoulli. Now let's go ahead and write it here. So my likelihood, since each and every one of these labels, images, are from Bernoulli distribution, making up binomial distribution, I have the joint multiplication of all. Don't get startled yet. Now this multiplication, and we're going to take derivative, we know for SGD to happen, but let's not get startled yet. And since, what is the P of this guy? It's yi, right? And I take it to the power of, this time, what is my label? My Ri. And 1 minus yi, 1 minus Ri. So that's the likelihood of my data set with respect to some parameter. You might, let me write below before you get lost, because it's very easy to get lost here. I see my likelihood, I can calculate my likelihood, R is here, but Y, let's remember Y was a sigmoid function of Z, and Z was nothing but W transpose H, and H was nothing but f of x. So that was it, what I had. Okay, so I have a cost function. So I have something to maximize. Of course, this is not yet a cost function. A cost function is to be minimized. But before we go with the exponentials and multiplications and products, let's take the logarithm of this likelihood. Logarithm is such a great function that converts all of these ugly exponentiations into multiplications and converts multiplications into summations. So that's my log likelihood. My log likelihood is equal to multiplications become summations. I equals 1 to capital N. So Ri comes here, log yi plus 1 minus Ri times log 1 minus yi. So that's my likelihood. And my cost function, I would like to increase the likelihood, right? Why can I take the log? Not because it's fancy and makes my otherwise difficult equations to be simpler. I can take logarithm because logarithm is a monotonic function. In a monotonic function, if you can find the maximum of a function, the same maximum holds in a monotonic function. So that's why we can incorporate this monotonic function. And for the cost, finally, my j, which is, again, we call this cost, is then not the likelihood, but the negative likelihood, right? So the negative likelihood, this is for TensorFlow implementers, you will find the cost as negative log likelihood. So in TensorFlow, this is how they call it, and it's a giant negation in front of this. Let me not write the subscripts plus 1 minus r log 1 minus y. All right, so that's negative log likelihood. And there is a there's a term for this. The other name for negative log likelihood is also called cross entropy. All right. By the way, that entropy term came to our usage because Claude Shannon was a very good friend with, I'm going to say von Neumann from the quantum mechanics field, and cross entropy is described as measuring the uncertainty, and entropy is also measuring something similar in quantum, but let's not get complicated so much. All right, so the next thing, so we have built the model, input to output. We have established our cost function. The next thing is to calculate, do the SGD, right? Stochastic gradient descent. So I know my d delta W is at dj over dw, right? Even if I take it one by one or as a vector, let's make it as a vector, I can calculate it similarly. So, but there are the j, inside of j, the w does not exist. So I'll have to calculate the dj over dy and dy over z and dz over dw. All right, so that's what we're gonna do. Let's go ahead and give the names, give the numbers, 1, 2, 3. Let's go ahead and do number 1 first. So again, calculate dj over dy, which is d over dy. Let's write summation I equals 1 to capital N. What was it? Y to the r. Let me not write the indices. We all know that these are these all take their own indices. And of course, there's a negative here plus 1 minus y to the 1 minus r close parentheses. All right, so which is equal to, again, I can take the derivative inside my summation. Whoop! Why? I confused it so much. I already did the log likelihood calculation. So it's going to be r log y plus 1 minus r log 1 minus y, close parentheses. So I'm taking the derivative with respect to y. The derivative of y is 1 over y. And again, let me not forget about this negation here, plus 1 minus r on the top, and this is going to become 1 minus y, but this negative y also gets its own derivative, so I'm multiplying it here. Let's make it a little bit more compact. So if I equals 1 to n, so I have yr, I'm sorry, on the top I have r minus yr minus y plus yi divided by y minus y. So the thing that I like so much, and I can incorporate this two inside. So I have I equals 1 to n, y minus r, because I used this negative to go inside, divided by y minus y. Okay, it's so that was one. So that's my first part in my chain rule. By the way, let me write this. If you remember from high school, so this is the chain rule. One core thing in error backpropagation is the chain rule. All right, so let's go and do the next one. dy over dz. dy over dz. What was dy? So d sigma z over dz. What was sigma z? d 1 over 1 plus exponential negative z. All right. dz. So if I take the derivative of the top, which is 0, times whatever, minus the bottom, the derivative of the bottom, which is exponential negative z, but the derivative of this makes this one 0 and makes this one positive, divided by the square of the bottom part. Exponential negative z close parentheses squared. So I have nothing but 1 over 1 plus exponential negative z times exponential negative z divided by 1 plus exponential negative z. So notice how this guy, I've already named this guy, this is nothing but y. And if this is y, this becomes 1 minus y. So the derivative of sigmoid is y times 1 minus y. All right. So one thing that you notice is that, so this is my step. I'm going to pause here. So I am calculating how much I'm going to make a step. And my y is my system's output. It's the probability that it is going to be 1 or 0. Notice that as y goes to one of the classes, as y goes close to 1, you think that this is going to go high, but this my 1 minus y term is going to suppress that. And similarly, as y goes to 0, this term is going to suppress that. Notice how this term becomes more emphasized as you get away from the asymptotes. And let's go ahead and write the last term, dz over dw. All right, and d h transpose w divided by dw, it's nothing but, whoops, it's h. So my delta w, which is my step to learn, becomes all of a sudden summation of all of the terms I equals 1 to n y minus r y times 1 minus y times 1 minus y, and this is from dy over dz, and this is dj over dy, and times h, whatever that w talks to, and all of a sudden it becomes exactly the same thing as y minus r. Okay, now let me use the parentheses, times h. Yeah, whatever the WC's multiplied with the error, like in the beginning. So, so far we have dealt with cross entropy, and we did our two-class classification as for the linear part of the model. Next, we are going to break the second cycle, second constraint, second simplification, which was dealing with only two classes. Let's go ahead, and in the next video, let's go ahead and make it k classes, multiple classes, and how the training works then. Hi. I named the title of this video the derivative of the softmax because that's what I'm going to be talking about in this video particularly, but it is actually building on what I have previously discussed. We have opened up our AI model, made it parametric, and established the parametric of the part that's at the ultimate layer, the final layer. And we simplified the problem into two chunks. One that was the feature extractor, and then the linear classification layer. At first, we started with a very nonsensical cost function, mean squared error cost function, for establishing a classification problem. And then we converted it to a two-class classification problem where introducing the sequence of labels or samples, our samples coming from a Bernoulli distribution, making up a binomial set of observations, coming with the probabilities that the model is going to infer. Therefore, we were able to make it into a maximizing the likelihood setup, which yielded us the good old cross entropy loss. Now we're taking into the next step. Now we do not have only two classes. We are talking about a k-class classification problem. And obviously, with k-class classification problem, we cannot even attempt to approach, well, we can, but it would not make sense with the absolute error cost function. We cannot try to regress the outputs to one of the k distinct classes. We cannot make it 0, 1, 2, 3, 4, 5, or some values that we can associate with these classes. Instead, we are going to keep approaching the problem with the same statistical approach. In the previous case, we mentioned that the two classes were binary random variables and make it binomial. Now we have multiple classes. we are going to convert it into multinomial distribution. And the softmax, which exists in the title of this video, is the part that our output is going to give us a probability distribution over this set of classes. So here we go. Let's go ahead and open up our notebook and let's put the title K class classification. All right, so in order to approach, let me reintroduce our setup again, but this time I'm going to make a little bit of difference. Right, so again, we start with our images. So that's my X, and these are all brain images here. And this X goes into this magical feature extraction box, and this is going to give me my H, and this H is multi-dimensional. The dimensionality has something to do with the capacity of the model. So previously, what we did was we took a weighted sum of these embedding dimensions, and we built a neuron like this and gave the weights 1, 2, 3, blah, 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 and named it Z. But now I'm going to take another color and I'm going to call this only Z1. And similarly, I'm going to regress to different Z's for different classes. So I will have, let me draw it a little bit better. Right below the Z, so I can have my Z2, and similarly, let me draw another one. So I will have one for each and every one of the Z's. So I have ZK. There's a name for these predicted activations for each class, and the name for this is going to be logits in a second. And from this activations, we previously used this and then used a sigmoid activation function to get the probability. Right now, these activations have to kind of talk to each other, give some information to each other, because there's one specific feature of a probability mass function is that they need to sum to 1, right? So I have now, I'm going to draw a block of the softmax function, and this softmax function is going to take as input all of the z's and then give me my y's, right? And these y's are going to be a probability mass function over the set of classes. So it's going to be high for one of the class, not so high, and a little bit high for some class that it might be confusing, mostly zeros for something else, and something for each and every one of the classes. So I can now define my, let me not call it yi, because I would like to use the subscript k for classes. So this k is going to be classes, and for each and every one of the inputs. And again, please note that there are many of these, like each and every one of these inputs with superscript I in my training data set or my test data set will go through this and then give me an H of I and Y of I K, and my Y of I K is defined as, so this little equation and the triangle on top of it is pronounced as defined as, hopefully, again, we're going to make it happen that it gives me the probability of the classes K among whichever K equals 1 to capital K, given x of I, right? So it's going to, given my image, our desired um, neural network or AI model gives me the probability of each and every one of the classes. So at this point, I'm going to stop and remind you a few things. One, practical information. So this YK, since it is giving you the probabilities, you can just take the maximum of it. And if these are the probabilities, well, most probable output should be this, and I use it as this, right? So it's like typically the maximum is used. This is not directly giving you the maximum. This is giving you a distribution, but hinting the maximum. That's one reason that this operation is called the softmax. And I will show you in a second how the formulation of the softmax is. But the other usage in mostly generative AI is that you do not directly take the maximum when you're training, when you're predicting the next, say, token in a sentence. You sample from this distribution. Like there are certain words that could follow the sentence that was just uttered, and the probabilities of these next words are as such our model predicts, and you sample one of them per this distribution, and then you continue using it similarly. That's why this part of the video is quite important, because it's quite generalizable. This skills that you will get from this video is going to be applicable in several machine learning platforms. All right. The second thing that I wanted to mention is that I would like you to notice what's going on in this little neural network. One thing you see with different colors, they are, let me take my black pen to describe what's going on here. My little, each and every one of these colors. So if I write the first one, so I have my W1, W2, W3, WD, if this one has dimensionality D. Otherwise, the inner product cannot happen. So that's going to be predicting the logit of the first class. And let me take my green, and there exists another row vector, W2. So I'm going to call this W11, W12, W22, W21, W22, W23, yada, 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 WD2D. And these are all one, meaning it's the first class's logit. And yada, 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 this gets appended with W K1, WK2, yada, 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 WKD. So now we are talking about a matrix. So that's capital W matrix. So that's my weight matrix that I'm learning. I'm going to do two underlines to represent it's a matrix vector. And my Z, which is a vector, is going to be obtained typically in neural networks with this operation WH. Of course, there is always a bias term as the implementer desires, and this bias term is also a trainable parameter. That's nothing to do, I mean, that's not so much to do with what we are explaining right now. So I'm going to simplify it, and bias can also be added, and this is called a weight matrix, right? So we're talking about a weight matrix. So previously, if you remember, we introduced a function that combines z to y, which was the sigmoid function. Right now, I'm going to simplify the problem by just writing it out. So my yk, which is the softmax, of z of k, and which is defined very similar to our sigmoid function, but again with exponentials, exponential to the z of k, and as I mentioned, the yk, it's a probability value. It has to be between 0 and 1. They have to sum to 1. So I am introducing the summation to the denominator. So I'm calculating the e to this of all of the classes exponential zj, right? So that's our softmax function. Let's draw a rectangle around it. So that's my softmax. And of course, softmax of zk doesn't only use zk, it uses the whole thing. So our next step would be to establish the cost function. Now, like our first job is always tie the input to the output. We did that. We just hope right now that it is going to give me the probabilities. But we learned from the k equals 2 classes, our second job is to build a cost function that is going to do what your heart desires, right? We need to establish a cost function that is going to be persistent with what you expect the output to be. We expect the outputs to give the probabilities of each class happening. But for that, I need to start by reintroducing the training set, because it's a little bit more different right now, because now we have k classes. So the training set is established, remember, our from previous for ith sample and its label. Well, right now my ith sample is and let me complete, and that's for I equals 1 to n, however many samples I have. So that's my image, and R is a one-hot vector depicting the class of x of I. Right now, we're not only cancer and healthy, we have pneumonia, we have COVID, we have all the medical terms that I cannot pronounce. So we have several classes. And what is a one-hot vector? A one-hot vector is a vector with all zeros, all of the zeros, but there's only one location that it is the class, right? So this is 1 at the index, and let me make it a 1 so that it doesn't look like index of the class of x of I. So in a way, this part is important too, since we're training for it to learn that it is actually coming from that class. The label for my probability mass function estimator should actually be a probability mass function too, which, when you look at it, a one-hot vector is a probability mass function of a certain event that's going to be happening. There will come times in the future that we will cover knowledge distillation. When we are talking about knowledge distillation, the label, the R, does not necessarily need to be a one-hot vector, a certain event. Sometimes we will be learning from the output of a bigger, more capable model, which we will call the teacher, and the little model is not going to use the true labels if they exist from the data set, but learns from what his teacher thinks about looking at the data, which is probably unlabeled. So in knowledge distillation, we make use of unlabeled data set using a teacher and teaching a student. That's going to come in the future, but I would like for you to just allocate a little bit of leeway or some space for room for elasticity when we are defining our labels here. And yeah, so right now the fact that it is certain event one hot vector doesn't mean that it is always going to be the case, but the math that I'm going to introduce right now holds for the knowledge distillation too. So like everything is going to be the same. So right now, since we are talking about a multinomial distribution, so my images are samples coming from their own classes, the likelihood, let me write, it is a multinomial distribution. What is it? My data set. Our data set is a multinomial distribution, right? So that's the one premise. So then what is the likelihood? So the likelihood, probability of my whole data set given the parameter of the model. So that's model. Since my model outputs, which I hope to be the probabilities, should explain my data set. And that's called the likelihood. That's the capital L for. And it is nothing but going over all of the samples in my data sets. So I'm going to lose the superscripts parentheses i's here for the sake of simplicities. I will add only a few of them here so that you can see what is where. And for all of the classes there in each and every one of them will have only one class. So like I will have to have my y of k to the r of k. So notice that in this inner multiplication, in the one hot vector way of r of k's, and notice these are all with superscript I, but let me delete this just to make things a little bit less frightening. So this looks a little bit maybe too technical, but not much is happening here. The y of k's are my model's outputs of what the probability of the kth class for a given input would be. And r of k is its label. It's either 1 or 0. So it's going to make them all zeros and then make the outputs disappear and only remain one of them, the pertinent class, right? And if I can predict with, which wouldn't be a good model, but let's say my model just predicts ones and zeros for the correct classes always. This is going to be my likelihood is going to give me a likelihood of 1. Anything that's predicting something close to 1 or far from 1 is going to give me something lower than the probability, right? And of course, I wouldn't want to work on this. The next step for me to take derivatives. And of course, I don't want to deal with this. I take the log of this because logarithm is a monotonic function. When I take the logarithm of this guy, all of the multiplications become summations, x and x. And for k equals 1 to capital K, and let me put mark because things can get very crowded and it can be lost at some point. So this is for all classes in 1 to capital K. and this is for all samples, for all samples in the data sets, right? Okay, if I take the log, I get, let me get my proper pen color, RK, YK, not YK, log of YK. And of course, we would like to maximize this, and we would, our cost function then would be the negative log likelihood, which I'm going to call my cost function. Again, this is my cost function, which is the negative of this thing. And I will try not to forget this negative sign as I go to go in the derivation, right? K equals 1 to K, RK log YK. And let's go ahead and also write what was what. Like this looks like it includes the x, but there's no x here. Let me complete what my yk is. My yk is exponential z of k divided by sum of all of the j in 1 to k exponential z of j. And my z of k is equal to wk transposed h, and I have many of them, and my h is nothing but a function of x. So that's still to be non-parametric. And let me say for now. And if I can draw an evil face here. Okay, so that's non-parametric for now. What does non-parametric mean? We are not learning anything about it. It is what it is. It was engineered, and we trust our engineers. We're gonna leave it. This is not going to be learned from the data, but very soon we will open up for it to be learned from the data. So for stochastic gradient descent to work, I would want to calculate the step for any of my weights, right? So my weight, I have k of them. Let's take one index, like n, such that it doesn't confuse with the index, because there will be several indexes. That's why I chose n, because there are i's that I always use for my dataset samples. The j that I use, you see under this softmax, so I don't want to use j. K represents the class. Sometimes we will be summing over the class as exists in our dataset already. In our cost function already, and that's why I'm using n. And wn, note that it is the nth row of my matrix. It's a row vector, and if I calculate all of the wn's, the step for all of wn's, which are independent from each other, I can find my delta w, the step for the whole matrix. Well, let's start simple. Let's continue simple. So my let me explain what this is. Step or optimal step or steepest descent step for the nth row of the weight matrix W. All right, so that's my that's what the n is from. And n, it can be 1, 2, 3, 4, 5, all the way to k, and we could have written 1 or 2, but let it stay n. So I know, due to the steepest descent, this is nothing but its derivative with respect to my cost, right? So dwn. But I cannot take it directly because the w doesn't exist, and I'm using the chain rule here, and so I can calculate dj over dy, and I can calculate dy over dz, and I can calculate dz over dw. And I know that my j actually involves all of the k values in it. So I'm actually calculating for all of the derivatives for the kth class. And I know from my image, I know all of the y's or all of the z's, they go ahead and contribute all of those k's in my y, contribute something between here to here, because this is a function, right? Through softmax, it changes the logits for all of the classes. So I need to consider all of the k's. They are not independent. Why they are not independent? Because here in the denominator, I'm going through all of them. So a little bit of change in yk for any of the k's will affect should affect the z of others as well, right? So I have this yk here, and since I am marginalizing over all of the k's, like summing through all of the k's, and this yk will have, these yks will have derivative with several of the z's, but I am only interested in wn, and wn is only connected to z of n. So I'm going to calculate the derivative with respect to z of n, right? So here we go. So we have 1, 2, 3 derivatives. So I have this, let's call it 1. I have this. This part is going to take you all the way to high school. Are you ready to feel a little bit of time travel, making you feel a little bit young again? All right, this part is going to take you to college, linear algebra, but because this one is a vector, this one's a scalar, this one's a vector. Okay, so let's do number 1. dj over dyk, which is d over dyk. Let's write what my j was, summation of all of the x's. So this summation, the summation over all of the x's exists everywhere, so I'm not going to keep using it. I have k equals 1 to k rk log yk. That's it. And I can take it to inside because derivative is a linear operation, right? So d over dyk rk log yk, and the result is going to be, and of course there's always a negative here because I'm calculating negative log likelihood, not the log likelihood. And if I take the derivative of this, I will get negative summation k equals 1 to capital K rk over yk. So that's number 1. And number 2, dyk over dz of n. Did I write it right? Yes. So dyk, let's write like this, dz of n. So that part is going to be a little bit, I hope I have enough space. If anything, I can introduce some more. Dyk, let's write what yk was, right? Instead of, in terms of its input. So yk is described as exponential of z of k divided by summation j equals 1 to capital K exponential z of j. Okay, this part is the part that the moment that you see three different indices in one equation, it means that the Weaver discretion is advised. You need to be very careful about what you're touching, what you're doing. So I have on the top the K index for the class. That's something to do with the YK, the probability. But I know the probability of the kth class, which is going to be summed here when I merge the two parts, has something to do with all of the logits. Because why? Because I have this the denominator, and I have therefore calculating any arbitrary calculating the softmax the derivative for any of the nth logit, any n. It can be k, it might not be k, right? So therefore that's the second one, different from the zk. And the part in the denominator of the zk yk calculation is the one that it's already covering all of the j's. So that's accounting there for all of the j's, right? So by the time that, for the sake of this calculation, n and k, the j is already used inside. All right, so we're talking about a derivative of a division. So the derivative of the division, we're going to take the derivative of the first part with respect to the derivant. The derivative of exponential zk with respect to z of n, well, it can be 0 or it can be exponential of z of k if n equals k and 0 otherwise. And there exists, let me open up a thought bubble here, there exists a function that represents that, delta function. So delta function, it takes as input some statement, true or false, and it gives you 1 if k equals n, or 0 otherwise. Or this is k equals n. I shouldn't say k equals n since I'm like introducing a general rule. So there's an expression. If expression true, right? If this holds. So I will, when I'm doing this calculation, right? So I'm calculating, I just wrote the first thing in my derivative. So it can be z of k or nothing if k equals n times the second part. I'm not going to write all of these j's. I'm going to right now, let me use my purple. I'm going to call this part, for the sake of simplicity, s for summation, right? Times s, the bottom part, minus the first part, exponential z of k, times the derivative of the second one. Okay, now the second one, summation for all of the zj's. It goes through all of the zj's, j equals 1 to k, and I'm trying to take the derivative with respect to zn. Zn exists in the summation. Everybody else disappears, but the zn stays. So I'm going to write exponential zn because everybody, all of the z1, exponential z1, exponential z2, z3, they all were 0 with respect to zn. and only Zn, which is a part of this J summation, remains and everybody else goes. So that's how the second term came. And the third term is S squared. So let me go ahead and write this a little bit simpler way. So I have exponential zk delta k equals n, which still startles me, looks like it startles me, but don't worry about it so much. It's doing its function and it's going to disappear in a second. Divided by s over s squared, so that I have this s minus exponential zk divided by s times exponential zn divided by s. So I hope so far you are able to see the harmony of what's going on, and we will move on to this in a second. And the third part is even simpler. The third was d over dzn over dwn, which is dwn transpose h divided by dwn, whoops, which is going to be my h, right? So actually this is going to be h transpose, strictly speaking, because h is a column vector and I'm interested in a row vector, right? But h, remember what h was? H was the input to w, right? And that's a little bit odd because for all of the rows, h is the same for the derivative. But let's go ahead and combine the whole thing. Wn is, let's combine, so I had the negative summation k equals 1 to k. What was it? Let's go. Rk divided by yk, open parentheses, exponential zk delta k equals n divided by s minus exponential zk divided by s exponential zn divided by s, close parentheses, and h transpose here. All right, let's go ahead and play with it a little bit. So my thing is going to be, I'm going to keep the negative here so that I don't get messed up. And I'm going to open up a big parentheses here so that I don't get confused. K equals 1 to capital K. I have Rk over Yk exponential z of k delta k equals n divided by s. And I have again a negative summation over k equals 1 to capital K. And I have the Rk over Yk here. And let's go ahead and simplify this. So do you see that this is nothing but Yk, and this is nothing but Yn. Here we go. Now we're reduced to two indices, but still scary. It's like every single time I study this. Wait, what was k? What was n? N is the row of the weight matrix that I'm trying to find the derivative for. K is iterated. K is all of the classes that's coming from the softmax. I have to cover all of the Ks. By the time this, please notice, there exists Ks here, but by the time these summations are applied, no K will remain. No K can remain. This K is the index of the summation already. And let's go and write Yk, Yn, and there exists all of them take 1 H transpose. Perfect. So one thing I like is I can go ahead and cancel these guys, right? So I have that's great. And one thing that I would like you to show that. So all of these, looking at this, so all of these RK, YK, so they're all going to take this index. It's going to be R1 over Y1 exponential Z1. But then when it is 1, K equals not going to be, 1 equals not going to be N unless N is 1. And the whole summation is going to disappear for that index. And K will going to be 2, and then this is going to be calculated, but this delta is going to kill it if it is not N. So would you agree with me if I tell you everybody disappears, but only one of the K's will survive this mayhem, this summation, and which is going to be only K equals N term will survive because of the delta K equals N. They will all disappear. So what I'm going to write here is equal to negative, open my parentheses, only the K equals N term is going to survive. So it's going to be Rn divided by Yn exponential Zn divided by S. And this delta is going to be 1 when it is there. Please, this part is important. If you did not get it, feel free to rewind and look at it one more time. And negative, you see that all of the K's disappeared? And I can take this Yn outside the summation because it's nothing to do with the summation. And inside the summation, I am left with nothing but Yk, H transpose. And drums roll, we're getting very close to the end. So would you agree with me if I sum all of the K values of my label from K equals 1 to K, I will get 1 because they sum to 1. It's a one-hot vector. It's defined as such, right? So and also let me do one more thing. So would you agree with me that exponential Zn over the sum is nothing but my Yn? So these guys will also cancel each other. So I will eventually have negative Rn over Yn H transpose, which is nothing but Yn over Rn H transpose. So that's for my weight matrix. So that's my weight matrix, and that's my Wn. And my Wn update is going to be H transpose, whatever it used as input, H transpose, multiplied with the error. The error, now I'm going to use the proper word, back propagated to the output of Wn, right? So that's the error, Yn minus Rn. And for all others, there will exist Yn plus 1 minus Rn plus 1, and all of them, right? So eventually, when we're talking about delta W, which is a matrix, is going to be the error that backpropagated. So that's going to be my error or grad. My grad is going to be y1 over r1, y2 over r2, y3 over r3, yada, 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 with an outer product with H transpose, right? And notice how the shape actually matches. So I will have a delta W, which is the same shape as the W, with as many rows as its outputs, makes sense, and as many columns as its inputs. And what I'm going to do, I'm going to subtract this W. I'm going to do my learning. My W is going to be W minus some learning rate times delta W. My dear friends, this was the derivative of softmax and how linear layers in neural networks gets updated with outer products.